Okay, everyone, welcome to the second session of this morning. It's a great pleasure to have Professor Alexey Bondal from Steklov Mathematical Institute. He will tell us about derived approach to high-speed categories. Let's welcome.
Thank you very much. Yeah, I mean to write down the definition of highest weight category, but okay, I was a bit late. So let me start from motivation, how this highest weight category showed up in mathematics. And this is about complex analytic geometry. So let X be a complex analytic space. Which, well, let's assume it's smooth at the beginning. No, it's not that important. And dx is the sheaf of linear differential operators. On X, or you can say on OX, homomorphic functions. And we will be interested in the category of dx modules with some extra conditions, and this extra conditions is regularity and holonomicity. So we'll consider regular holonomic dx modules. Before giving, I mean, I might not go into details of the proofs, but of definitions, but let me just show you an example of this. The one is, say, assume X is just a complex line, C, and nabla is a differential operator of this form. This is a linear differential operator on homomorphic functions because you can multiply by this guy and differentiate by z, and then take the difference. So M is the corresponding, D module. It has the form of dx multiplied by nabla, so to speak. Even though nabla is not in dx itself, but this makes sense. So one example, and the other example is just take z itself as a differential operator of degree 0. So the module M here is dx multiplied by z. So you see, regularity is something about behavior of horizontal sections for this nabla. In particular, if it has logarithmic singularity like this, then this is regular. But if you take alpha over z squared, it's no longer regular. So regularity is more or less about having poles not greater than 1, though it's not quite correct. There are some examples of regular connections where you have high poles, but nevertheless the behavior of horizontal sections, the growth is good enough. And holomorphic, holonomic, this is whole is about holonomic demodule. These both are regular and holonomic. So the holonomic demodule is about, it's about what's called singular support. Where is Andrea? Yes, is it called? Okay. Anyway, let me just formulate it this way. These modules, they have so-called singular support, which is a subvariety in the cotangent bundle of X of M, and the singular support is involutive variety, and if it's smallest one, meaning Lagrangian, so this guy is Lagrangian, and this corresponds to have holonomic demodules. Well, very informally, it's just one equation. That's why it's holonomic. This is also one. It's holonomic, more or less like this. So it's, but if it say was two-dimensional variety and you have only one equation, it's no longer holonomic. I mean, maybe you studied at the kindergarten, right? So this should be Lagrangian submanifold in cotangent bundle of M, considered as a symplectic manifold. Now, there is so-called, shall I introduce something else? Yes, we can also consider the category of sheaves on X, and the sheaf C means it's constructible sheaves. So it's constructible. It's another category. So this one category, this another one. Constructible sheaves of C vector spaces, finite dimensional vector spaces of C vector spaces. Dimension finite, which are constructible with respect to a complex analytic stratification. At this moment, stratification is not fixed, but when I speak about highest weight categories, I will fix stratification. So maybe I'll formulate the statement for which is already kind of classical, about 1987, 1988. But I will give another proof for it from the point of view of derived category approach. So, but I will formulate it right now. Maybe on this, maybe here. So the point is that these two categories are equivalent, but not quite equivalent. They are derived equivalent. So, but maybe I will now fix stratification. Yes, it's called Riemann-Hilbert correspondence. Derived category of this holonomic D modules, holonomic with regular singularity D modules. First track, right? It is bounded derived category is equivalent to bounded derived category of this constructible sheaves on X. And the main point of perverse sheaves that we consider here, the subcategory, abelian subcategory of these modules, and ask what is the image under this equivalence. And the answer is perverse sheaves on X, which is some abelian subcategory here, but it's not just this constructible sheaf. That's the main point. And actually here it's better to consider on both sides, actually. It's better to consider, sorry, so regular holomorphic holonomic is better to put here, and this C also better to put here. This means that we consider complexes of dx modules with regular holonomic cohomology. I mean, complex has a cohomology. These are just D modules. These D modules should be regular holomorphic. And here, analogously, we consider sheaves, whatever sheaves of, say, C vector spaces on X, and we require cohomology sheaves would be constructible, like I defined it here. All right. So then we have this category here. Still, you have this here T structure. The heart of this T structure is the abelian category of DS modules. We look at the image of it, and this what is called perverse sheaves on X. They of course could be defined more straightforwardly, but the idea of perverse sheaves is this. And now the point is that if you fix stratification and consider modules which are somehow subordinated by the stratification, complex analytic stratification, and here consider constructible sheaves which are also how it's called smooth with respect to the stratification, then you have the category of perverse sheaves will be highest weight categories, the main subject of my talk today. Okay, so maybe I formulate this statement. about fixed stratification. So now X is still complex analytic manifold, but now maybe I'll write it here. So we consider fix on X a complex analytic stratification, meaning Whitney here, right? No, I don't know. Sigma, so all strata are assumed smooth. And we put some partial order on the strata, and one stratum is less than or equal to the other one if and only if S1 belongs to the closure of the S2. Then we can consider, yes, and there is two conditions which I put on this. One is that all strata are contractible. And second condition is that S bar minus S is a Cartier divisor. Or empty, if not empty. By Cartier divisor here, I mean this thing. So if you consider this this thing as bar minus S as something closed inside S, then it should be locally given by one holomorphic function locally. Okay. Function. So under this condition, there is a theorem which claims that category of perverse sheaves with respect to this stratification sigma on X. But perverse sheaves, I mean, yeah, together with this partial order which I denote lambda, it just the set is just the set of strata with this partial order. So this pair is a highest weight category, which I will write just HW cat. And moreover, we have a derived equivalence, derived category of this perverse sheaves, bounded derived category of perverse sheaves on sigma. You can here just take derived category of the abelian one is equivalent to the derived category of this constructible sheaf with respect to this stratification. Constructible sheaf with respect to a given stratification is a sheaf of finite dimensional vector spaces such that if you restrict to any stratum, it is locally constant sheaf. So, but here we consider it, yeah, actually we can put it here, right? So you can consider sheaves, whatever, sheaves with compact constructible with respect to a given stratification. So these are sheaves of finite dimensional vector spaces, and this also, but these are perverse sheaves. These are actually complexes of sheaves which you get under that equivalence. of Riemann-Hilbert correspondence. Okay, so but I didn't say what is highest weight category, and this is what I planned to write down in advance, but didn't succeed. So let me now come to the austerity of algebraic category theory. So we start from an abelian category, and we put many finiteness conditions on this category. One is that it's Hom and X1 finite, meaning if you take any two objects in this abelian category, then Hom spaces of this K are finite dimensional, and the X1 is also finite dimensional. The category is of finite length. That means that every object has finite length, and this means that every object has a filtration, finite filtration, with the graded factors being a reducible object, which I call simple object. And that the number of these simples is finite, simple object. This is not necessarily conditioned, just to simplify the situation. Somehow I am going to consider some fundamentals of the story, fundamental ideas about this. So I just put this condition. I mean, people who work in representation theory quite often don't have this. There's some little more technicalities which I would like to avoid. So now at the line finite, what we call, yeah, I forgot to say, I guess, that this is this is a joint work with Agnieszka Bodzenta from Warsaw University. So we call the line finite category, which satisfy all this finiteness condition, and also which has a projective generator, meaning projective object, such that for any other object you have non-trivial morphism into this object. If you have this generator, well, Deligne studied this kind of category. It's actually extra finiteness condition, might be sound surprising. So all these are finiteness condition on the categories which we consider. So if you consider endomorphism algebra of this object P, then the category could be identified with the category of finite dimensional modules of this algebra, right modules. Now, under all these conditions, I would like to define what is the highest weight category. So, highest weight category, this is my abbreviation, is the following. It's by definition, A is satisfy above conditions, and that's highest weight. If, as meaning, so A is the line finite. I forgot to say, sorry. It's about A and lambda. So A is a abelian category, right? But lambda is a partially ordered set, a partial order, so it's poset structure on simples, on simple object. Of course, we consider here a simple object up to isomorphism. Yeah.
Object in the perverse category, shouldn't they naturally satisfy themselves? If you have analytic stratification like that, by the perversity, shouldn't you have this? Obviously.
No, I don't think it's true if you don't put these conditions in general. No. Yes, Beilinson is more about similar equivalence, but when you don't fix stratification, then it's, I think, Beilinson theorem. But if you fix stratification, it's a more subtle thing whether it's equivalent or not. So if you have this condition, it's true, and it's basically, I think, maybe that it's at least its highest weight category. Maybe not this, but it was proven by Mirolla, Villanin. And so it's 87, sorry. and the other one is partial Scott.
Is this result well defined on families?
I didn't think about this. I didn't think about this. Sorry, don't know answer. So what we have another proof. It's just one of example of application of techniques which I'm planning to. Yes, stratification is fixed for sure, because otherwise you wouldn't get highest weight category. And I announced the title of my talk is about highest weight categories. But highest weight category is not about just abelian category. It's abelian category with some partial order on simples of this category. It might happen. There's different highest weight structure depending on the process structure, or it could be no highest weight category. Depends. Really depends on the process structure. So. Right. So on simples name. So we have, so the definition is a bit strange. That's why I plan to explain what is our categorical approach to this definition. So there exists some object delta of lambda in A for any lambda in this poset lambda, such that first there exists an epimorphism from delta on lambda on L on lambda. L on lambda are simples, so we have lambda in A, we have L lambda simple object for lambda in lambda. It's just notation. So this is an epimorphism such that kernel has a filtration by simples with could never remember with graded factors. Kernel has filtration. Kernel of this morphism has filtration with graded factors. L mu by simples such that mu is less than lambda. Yes, mu is less than lambda. That's one condition. And the second condition, I have space for it. There exists, so we have, maybe I forgot to say, in this situation, we have projective object, but this projective object could be, we can the minimal one, which is P of lambda, where P of lambda is a projective cover of L of lambda. That's the usual story of this abelian categories. So we have this epimorphism from P of lambda to L of lambda, and now we take this kernel has filtered to delta on lambda. Sorry, there exists not this epimorphism but another epimorphism. So delta is mapped in this, but P is mapped into this. The composition is that morphism. So the kernel has filtration with graded factors, but now graded factors are the delta of mu, and mu is greater than lambda. All right. Kind of, I could never remember this definition because it made no categorical sense for me, and it's part of my talk is to explain the meaning of this definition. But maybe first I should say there is a dual version, which is equivalent to this one. So it's auto-dual somehow notion that there is also objects number of lambda and maps are in the opposite direction. So these guys are called standard objects delta. These guys are called co-standard objects. So there's two sets of standard and co-standard objects. So this is highest weight category, and the claim is if you fix filtration, then you have highest weight category and you have these direct equals. Okay. Yes, you're right. It's better. Well, I will speak about general theory, but you're right. Maybe to have this kind of statement, it's better to take characteristic to be trivial, right? At least algebraically closed field for sure. Right. But I will speak about general story, and will be applicable actually to finite characteristics and even to some relatively new results about Grassmannians. In finite characteristics, there is some highest way structure, but I'm not sure I have time on this. Now, how I plan to how I will explain this structure. So it's about abelian categories, right? Highest weight categories. But my explanation will be via exact categories. So let me recall shortly what is an exact category. Which I will always denote by E. If it's E, then it's about exact category. So one have to fix a class of class, I denote it by S, of conflations, conflations. These are like short exact sequences, but because, and this terminology, conflations, inflations, deflations, due to Bernard, I believe, right? Which is indeed very convenient, much better than Gabriel. It's Gabriel. But Gabriel worked with abelian categories, not exact. Exact too? Okay. Okay. With rest to you. All right, so it's more or less like short exact sequences, but because it's not abelian category, I don't write zeros on both sides, just write this way. So is I, this, so this is conflation. This guy will be called inflation. And this one, deflation. First, so we fix some class. It should be so-called kernel co-kernel sequences. Which means that I is the kernel of this morphism. Yeah, category is additive. I is the kernel of D, and D is co-kernel of I. So we fix some class of kernel co-kernel sequences, and they should satisfy several axioms. One is that I believe this actually looks like a very formal thing, but I believe actually that in 21st century mathematics it will take its very important role. So now X, this is belongs to this class, so it's a conflation. Then the second axiom, the composite of deflations, the composite of deflations it is a deflation. Next is a pullback of deflation exists and is a deflation. So if we have some deflation like this, and any morphism F from some W, then the fibered product exists, which is Y cross W over Z. First, it exists. And second, this guy D prime is a deflation. And similar statement, similar axiom, let me write it here, X3. Because of space. Similar statement about inflation. So if we have inflation x to y and any morphism f here to w, then there exists a cofiber product, which is y over w over x. First, it exists, and second is I prime. So I was inflation, generic say. So this was deflation. This is inflation. And I prime is also inflation. So this axiomatics is due to Quillin, though Quillin introduced some extra axiom, which was actually it was proven before a long time ago by Yoneda maybe, but then reproven by Bernard. Anyway, so we don't need this axiom. So what is the point? I mean, from homological point of view, these exact categories are important because you can define derived categories of them in the same, more or less the same way as you do it for abelian categories. So if your E is exact, then derived category of E, bounded or whatever, exists. At least unbounded exists. So somehow a homological algebra is applicable to exact category. The difference is if it's abelian category, I mean, abelian category is a particular example of an exact category. If it's an abelian category, then in the derived category, you have so-called T structure, I mean, canonical T structure. And in D of E, you not necessarily have any T structure at all. Okay. Now, yes, so now I want to understand this definition by means of exact categories. So I raised this theorem, but it will follow from one of our criteria. So exact categories, so I should introduce two kinds of, two definitions. One is some particular class of exact categories, which is thin categories. And the other is some process how to make a abelian category from an exact category. It will be so-called right, what we call right and left envelope of the exact category. So, and this only the first half of my talk. How much time do I have? 10:45. Okay. Okay, maybe I'll explain shortly as much as possible. The point is that, you know, if you have triangulated category D, then there is a notion of semi-orthogonal pair or semi-orthogonal decomposition, SOD. It's a pair of subcategories T, let me denote by T and F, such that T is admissible left or right admissible subcategory. So it means that home from T to F is trivial. And also every object in D has a decomposition in T and F, where this guy belongs to here, and this guy belongs to here. If such a decomposition exists, then it's actually unique. This is our triangulated subcategories. So this is a definition of semi-orthogonal decompositions, which you could see on several talks on this conference. But now there is some similar thing which is called, so for abelian category, there is a notion of torsion pair. Which probably you know by similar TF in this abelian category D. And this is very similar property. Homes are trivial and similar short exact sequence, right? Am I right, Bernard? Right. But now I would like to define something similar, but for exact categories. And surprisingly, there is two versions for this. One is exactly the same, and this is what we call actually, but this is, so same definition. What is called, we call it weak admissible subcategory. It's about T side. Weak right admissible subcategory. So it's about pair. It's T and F. We take F to be right orthogonal to T, and we require every object E. So we're speaking about weak admissible subcategory T in E. It should be fully exact subcategory, first of all. It means that it's closed under extension here, and exact structure here is induced from exact structure here. Fully exact. And it's full subcategory. So I consider this kind of subcategories. So now it's called weakly right admissible. If you have this, if this is a torsion pair or semi-orthogonal decomposition in this sense, meaning every object E in this category, curly E, is decomposed into T and the object in the orthogonal, sorry. So this is definition of F. So this is an F, this is an T. But surprisingly, this, as I said, we call weakly right admissible, because somehow to define highest weight categories, I need a stronger definition, and that's what we call just right admissible, similar T in E, fully exact subcategory. So right admissible. When you have the same property, but when we consider F to be, sorry, here, let me put here 0, because it's about only home orthogonality. But let me define F T. Define now F to be T perpendicular category, which means that we not only homes, but only X1 to be trivial. Well, first of all, if you have exact category, then you have not only homes, but you can define X1. In principle, you have defined high. Home. Yes, here is home orthogonality. And now I define perpendicular category, and it's a category, it's objects E in E, such that home from T to E is trivial, meaning from any object of this category T, and also X1 from T to E is trivial. X1 is well defined because somehow extensions are these conflations. Okay, so now I require, for right admissibility, I require TF to be a torsion pair in that sense. So it's stronger condition. Then one can define filtrations. So I want to define some, for exact categories, an analog of a full exceptional collection and triangulated category. And I claim that this, I will get something which is equivalent to highest weight categories. Question? So this I will call by thin categories. An analog of a full exceptional collection in triangulated categories. What is an exceptional collection? It's just collection of objects. It's actually a sequence of objects, and you can define some filtration with respect to this sequence. So this thin category will be defined by means of some filtration. So it's Hom next one. E is not E, but yes, E is Hom next one finite. And then E is thin, is definition. Thin exact category. Yes, exact. If there is a filtration, there exists a filtration by fully exact subcategories. With graded factors. Which I define this way. So this, because it's about categories, I should explain what are graded factors. We just take perpendicular category to ti minus 1 and intersect it with ti. So this graded factors should be equivalent. Ei should be equivalent just the category of finite dimensional vector spaces over K. So you can see how similar it's to exceptional collection. If you have exceptional collection, you got such a filtration, and the graded factors will be derived category of vector spaces. Here it's about exact categories. Because I take perpendicular, it's more. If it's just a pair, this filtration would be exactly what is this torsion pair for perpendicular category. So it's about admissible. So it's an admissible filtration, let's call it this way. Then the definition is that it exists. Then we can define irreducible objects, EI. These are objects, these are subcategories of our original category, everything just inside category E. So we can define EI as objects which correspond to K in these vector spaces of K. These are actually, one can show you that if you have such a filtration, then EI are the only simple objects. Maybe I'll call E lambda. Okay, no, here it's full order. EI is the set of simple objects, all simple objects, up to isomorphism, of course. And moreover, one can prove a theorem that if you have E is a weakly idempotent split exact category, and F in E is left. I don't know why it's left, not right. But anyway, there is similar definition of left admissible, say perpendicular. If T is is right admissible, then F is left admissible, and it's left admissible. Then derived category. Then we have derived category of E has a semi-orthogonal then SOD, semi-orthogonal decomposition in derived category of F and derived category of T.
So in the talk of Daniel, that author, would you think that because we didn't have this X finiteness, right? Is this more general than that, or is that more general than this?
It's about highest weight categories, first of all. He didn't say anything about highest weight, did he? But you're right that he doesn't have this one of finiteness condition, which I said is not very important, the finite number of simples, because if you have a stack, typically you have infinite number of them. Yeah, I'm going to speak about coherent sheaves too. Let me come to this point. Anyway, so we have this derived equivalence. So in particular, if you have this longer, I mean, as a consequence of this filtration, you also have a derived category of E will have a full exceptional collection. And actually, so if E is thin, then derived category of E has a full exceptional collection. Let me skip the definition. And this actually consists of EI with this order, which is given by this filtration. I mean, this object EI. And now the claim is that given a thin category, I can produce a abelian category, and it's actually one-to-one correspondence. Well, you just can think about idempotent split. Every if you have an object and idempotent and the morphism of it, then it splits in the sum. Object is split in the sum, and the idempotent is the project. Weakly, it's just a weaker condition, meaning beta state. Just beyond this. It means that if you have retraction, yeah, not all idempotents need to be split, only retractions. Those which could be constructed from retraction. It's just little technical detail, not important. Now, what else? Right, so now I need to introduce, to explain this highest weight categories, I need to introduce our definition of abelian hull. Given an exact category, E. So E is always exact. So you can define abelian hull, right? No, not hull. We call it anvil, not to mix up with the exact hull, which is already considered by mathematicians. So E is an exact category. So it's left, right, left, abelian hull, envelope, sorry, is a universal abelian category. I denote this right abelian envelope by AR of E, and it's universal among all functors into abelian categories, which are right exact. Everything, all functors are right exact here. In other words, it's such a morphism to be a little bit, because it's a categories. Categories make not category, but a two category, right? So one have to be a little bit more careful. So one should speak about right exact functors from, say, from AR to E into A. So for any A is abelian. So this IR should composition with IR, or precomposition, what's called, should identify, I mean, not identify, should give an equivalence of categories of right exact functors from this to this into right exact functors from E to A. That's a precise definition. But it's more or less the universal right exact functor from exact category to an abelian category. Or you can consider left exact functors, and then you have a similar definition. Now, the claim is that, well, first of all, there is a notion of exact hull when you consider everything is exact here. This was constructed by Adelman and Stein. They prove this exists. This one does not exist in general. There we have a counterexample. And when it exists, I still don't completely understand the story. For instance, I don't know example when this functor is not exact. If it exists, that this functor is not exact. And there is some other interesting technical details. And a very interesting question, how this left and right exact hull related to left envelopes, how they are related to exact hull. I think what people do in representation theory should be kind of invariance of this kind of picture when we understand it. So, but this is a new subject. I'm saying this could be generalized to thin categories. I mean, this is just for a pair, right? And if you have a filtration, longer filtration, then you have similar decomposition, but all these guys will be derived category of vector spaces because of this definition. Now, the claim is, so this is an interesting story by itself, and I'm surprised I didn't see this definition anywhere else. If anybody saw it, please let me know. So the claim is that, let me formulate it shortly, that exact categories is exactly the same as highest weight categories and the transfer from here to here is to E you assign right in exact envelope. And in the opposite direction, if you have a highest weight category, you can consider a subcategory of objects which have finite filtration by these EIs. Is it clear who are EIs? Wait, here is highest weight category with lambda. So assume we already have highest weight category. So we have there this object delta I, and delta, so we can consider, so opposite direction, we assign E to be what's denoted by F of delta I. So we have this highest weight category A with this partial order. So we have this object's how it's called standard object delta I in the definition is still there, right? Delta on lambda, but okay, just not a different notation. And we consider subcategory of objects which have filtration with graded factors in delta. It actually goes back to Ringel, I think, and maybe Dlaper, to consider such a subcategory. And this is actually a thin exact category. One should, I would like to warn that these objects EI, which are simple objects in this exact category, are not simple objects in the abelian envelope. So this is some kind of, they are, you see under this description, they are deltas. So this is an equivalence, so we can understand highest weight categories in terms of exact categories. But of course, we have also AL of E, left abelian envelope. And one can ask, what is this? And the answer is it's left and right abelian envelopes are related by so-called Ringel duality. So maybe I will be very short about this because I wanted to say something else. So Ringel duality is something which is kind of exchange these two guys. I can say more precisely, but and how it actually Ringel duality acts on exact category is also interesting. But I have only 5 minutes. Let me better to say something else. Sorry? Partial order, or you mean, or this full order is there is a canonical partial order on I just don't want to write formula, but there's some vanishing, non-vanishing conhomes, and X gives some canonical partial order, so you can, yeah. And this partial order, I mean, this full order, which we get from whatever choice of this filtration, of this filtration, this is full order. This full order is compatible with that partial order. Yeah. Sorry? What?
What is the factor to the lab? It's just
What is it? Huh? What you mean this direction? Yes, it's a subcategory with which is generated. I mean objects which has filtration with the graded factors delta i's. Ringel duality typically is this. You take this category, intersect with similar category for nublas, I mean standard and constandard. This gives you a characteristic tilting object, and then the morphism algebra of this characteristic tilting object is highest quasi-hereditary algebra. And quasi-hereditary algebra, maybe I had to say it here, that in the morphism of the projective of the highest weight, projective generator of highest weight category is a highest weight algebra, is a quasi-hereditary algebra. It's equivalent. So somehow Ringel duality, it looks different, but you can transfer one into another. And actually this characteristic, yeah, let me say this. So let's T is intersection of this category of delta i's with category of nabla i's. This is, and it's just, it's a category is finitely, additively finitely generated. So there's, if you take the generator of this category, additive generator, that this will be characteristic tilting object. So we have T here, a characteristic tilting object. And I think, I don't know how Ringel formulated, probably this way. If you take algebra A of in the morphism of this T, then A mod A is the highest weight category again. And so Ringel duality transfers from original highest weight category to this new one, modulus over this. Is it his standard way to explain this? But I'm saying it's actually about transfer between left and right. Okay, so maybe I skip. I also have some criterion in terms of pairs of exceptional collections for highest weight categories, but I have no time for this. Maybe I'd better tell a little bit about geometric application. So here I consider surface contraction. So X and Y smooth surfaces. And F is birational morphism. Then we consider null category. These are objects in derived category of X, such that RF low star bounded derived category of coherent sheaves on X. So it's about algebraic geometry now, such that this is trivial, and we have similar category AF, where A is just coherent sheaf on X, but still with the same derived property. So this one we call triangulated abelian category, triangulated null category, and this is abelian null category. The claim is that if it's smooth surface fibration, then well, for this criterion which I kept, so we have actually first derived category of AF is equivalent to CF, and second, AF is the highest weight category. And then you may ask, what is this Ringel's characteristic tilting object? And it has nice property. I mean, it's easy to describe it. I don't know how to describe the projective generator, but characteristic tilting object has a relatively simple description. And that would be basically the end, except for some consequences. So, well, maybe I will also describe deltas and nublas, and this is OR1. How much time I have? Oh, I overcome already. Yes. Too sorry. Okay, maybe I will describe just the tilting generator. So the tilting generator is ODG, ODF, where we decompose this morphism F into G and H, also birational morphism that is smooth. Everything is smooth surface here. So we decompose it and take the sum of these guys. What is this? These are discrepancy divisors for these morphisms. So the claim is that this is this tilting generator, and it implies in particular that the schematic support of the null category, so let me write it this way, schematic support of CF, so it's a consequence of the statement that schematic support is the discrepancy divisor, DF, if you know what that is. And conjecture is that it's actually true for any dimension, but only for smooth surfaces, smooth varieties. Birational morphism of smooth varieties should be also true. Of course, it would be interesting to generalize for non-smooth, but this I don't know how to formulate even. Thank you.
Thanks, Professor Bondal, for the great talk. Any question?
T. Here. So we consider. Sorry? G is this map, so dg is some divisor in X. Defined by G, correct. So we take structure sheaf and twist it by the discrepancy divisor of the whole F. That's correct, but why not to twist by, I mean, this is a coherent sheaf on X. DF is the biggest one, exactly, and that's why the schematic support is DF. Because you have, in particular, when you take G equal to F, meaning this is identity, you have just ODF of DF. And this is sheaf which has the biggest support, the discrepancy divisor. Yeah, actually, that's some subtle point. I would better say local schematic support. There's some issue. Let me write here local because I didn't write down all details of the schematic support. But for local schematic support, it's not difficult. So if you have some object A, and you say in derived category of X, right? And you may ask, what is the support of this object? You just consider morphism from OX to local endomorphisms of A, derived local endomorphisms of X, and take the kernel. It's some ideal sheaf, right, of some scheme Z. This Z is the schematic support, local schematic support of Z. Why I say local? Because locally, it is true that this object push forward along the embedding of Z into X. Meaning this object A, locally, not globally, is A is I low star of some object A prime on Z. But globally, it's not true. So to define, but this fact is actually global if you define this global support, schematic support in the right way. But this requires some techniques which I haven't written down yet. As a union, huh? As what? Right, it's for a given object A, right? But if you just the union of all of them. Mm-hmm. Yeah, thank you for good question. Yes.
Names kind of suggested that from representation theory, if you take like the vector models with highest weight representations and generate complexes of that, is that a highest weight category? Or so if you take some representation and to the highest irreps, you can associate a vector bundle.
Yes.
And then you can build complexes out of that.
Vector bundle on what? Sorry. On homogeneous space. Okay. Yeah.
And you generate via this vector bundle that gives you like some derived category. Would that be a highest weight category or where does the name?
I mean, it's abelian category. It's not derived.
Yeah, maybe I have a similar question. So it seems to me that the highest weight comes from representation theory.
No, originally it comes from what I said, from Hilbert. Yes, the word highest weight certainly comes from when you consider the category of semi-reductively algebra G. Yes, yeah, go ahead.
And yes, do you have some possible application?
In that, we have application which I didn't write down, and we actually didn't write it down on the paper yet. There is, when you consider Grassmannians, I mean, you know, as you said, you might relate this representation theory to, well, it's about D modules. No, it's not about. I have another algebraic geometric application. It's about Grassmannians of KV, but over some algebraically closed, say, field of finite characteristic. Characteristic SP. Then there is two papers, one by Vandenberg, Buchweitz, and somebody else, and another by Efimov about, first, in characteristic zero, there is an exceptional collection constructed by Kapranov. I mean, and that strong exceptional collection, meaning it's obviously highest weight category, but in characteristic P, it's more complicated story how they prove that it's highest weight category. And from our criterion, which I didn't write down, it follows, the result follows. And Efimov did some similar thing, but even over integers. So, but it's also not new application. This is new. But your question is about, you know, category O is equivalent to the category of D modules of, again, of Grassmannians, so homogeneous spaces, but subordinated to the filtration by Schubert cells, right? So in that sense, yes, it's about the same story. It's Brilliant-Bernstein theorem, right? So it's equivalent. It's a highest weight category, which is equivalent to D modules over perverse sheaves.
You said you're going to give us derived sense? Derived categories.
Derived sense?
Yeah.
No, I didn't say.
Ah.
No, I had, when I wrote the title of my talk, I had no time to think for long. Actually, I have an application, not application, some criteria for highest weight categories in terms of derived categories. Want me to describe them? It will take time, I'm afraid. It's in terms of two exceptional collections. I don't know. Does it make sense? Maybe people type. No? Okay. So. What? Then let's bet maybe I tell you.
Yeah, maybe it's